Hey everyone. Okay, so looking at that last video, it looks like there might have been some video quality issues in there, and I apologize if the video got a little bit choppy partway through. So I've adjusted some settings, and hopefully the video quality on this is going to be a little bit better and is not going to be breaking up on us the way it was. Anyway, so taking a look at the model. So hopefully at this point, you've gone through the first video, and you've gone ahead and you've created yourself a difference watershed model that can produce a differential watershed uh, within the area that we've got some data for. So the next thing we're going to do is we're going to take a look at the rest of the data that we've got, and that is going to be land cover data. So now if we take a look at if we take a look here at the data that came along with the zip file, you're going to notice that there is a 2001 NLCD and a 2019 NLCD. Now, the NLCD stands for the National Land Cover Database. I'm going to go ahead and add these in here. In fact, I can go ahead and turn off my difference watershed. And so I've got National Land Cover Database values for both 2019 and 2001. I've gone ahead and included these in here for you. If we take a look, let me go ahead and zoom out to this layer here. And you'll see, you'll see that this is a subset. The land cover database is, of course, it's national land cover database, so it's quite big. What you're going to see here is that these are in kind of an interesting skewed kind of rectangle. The reason for that skew is that rasters are always in a rectangle, but the issue here is that these layers are in a different projection system from the project as it is right now and the other data layers. So that's going to come into play a little bit later. We're not going to worry too much about projections right now. But just keep in mind that's why these have kind of a weird shape to them as they do. Okay, well, let's take a look at the source data for the NLCD, and this is the MRLC. This is the Multi-Resolution Land Characteristics Consortium. You can see that there are a number of different agencies that contribute to this, and as you can imagine, generating land cover data for the entire nation is a mammoth undertaking, and so it takes the resources of multiple agencies to go ahead and create these. You can see that these are available on different regions or North America in general, and they are available for different time periods as well. The reason why I'm even pointing this out to you is I've included data for this module. That's fine, but we are currently working on our proposals for our semester projects, and I want you to keep this data source in mind because a lot of you will probably be working with land cover data from some of the proposals I've seen. So going to the MRLC as a source is, it's just a good initial source. We can see we're going to be interested. There's different versions of this. There are future projections for land cover. There are time series and trends. We're going to be going to straight land cover data sets. Different years available, and you can see that we're going to be using the 2019 and the 2001. And if we take a look here, I'm going to take a look at the information for the NLCD, again, the National Land Cover Database. I'm going to take a look at the legend. And if we take a look at the legend here, we can see that this is classified into the rasters that we have on our map. If I go ahead and I use my info table here and I click on one of these bright spots here, I can see that, okay, I've got a band value here of 95, and my value in the 2019 was 95, 2001 was 95. Similarly, if I click around, I can see different values. So let's take a look at this 95. What's this bright value that's shown up here? And if I go back to my legend, and if I scroll on down, I can see that 95 is emergent herbaceous wetlands. So you'll also notice that the colors available in here will provide a nice colored version of the land. And what I could do is I could go ahead and go into my symbology, and since I really want this to be unique values, I could go in and I could classify, and I could go ahead and look for 95, and I can color this. And I could ask you guys to go ahead and color each one of these classes into the color that would match what we're seeing here on the legend. But actually, there's a better way to do this, and that's because I have already included in the zip file for you here a style file. So if you go ahead and you load up the National Land Cover Database style, you'll see that this will go ahead and let me turn off the 2019, and there we go. We can see that has very nicely gone ahead and colored up the 2001 version of the raster. Now it's the same. The legend doesn't change through the whole NLCD, regardless of which year you download. So let me go ahead and turn off those streams because it's kind of getting in the way. So actually now what I can do is I don't even have to go into the whole legend and everything. I can go into my styles here. And actually what I want to do is I want to go into my 2001 and I want to copy its style. And then I want to go into the 2019 and I'm just going to paste that style. And since the style is being defined externally by a style layer, it's going to apply just fine to here as well. So now we can see very nicely here, we can see if we toggle between the two, we can see a really good representation of change between the 2001 layer and the 2019 layer. Okay, so this is going to put us into a good position to go ahead and do our analysis. What we're going to do here, the reason why we've got 2001 and 2019 is what I want us to do is I want us to analyze change in land cover over this 18-year period. And we're going to do it for specific watershed boundaries, but we'll get to that towards the end of this video here. So in order to do this analysis, what we want to do is we want to go ahead and specify, first thing I want to do is I want to specify out the specific land cover type that we're interested in. I'm going to go ahead for the case, since I've already gone ahead and clicked on 95, I'm going to go ahead and I'm going to work with wetlands. In doing your analysis for Module 5 here, I actually want you guys to choose any other land cover type other than wetlands. I want you to choose something and run the analysis on your own, and we'll be able to see what you come up with. So let's go ahead. I'm going to run mine for wetlands. So the first thing I need to do is I need to pull wetlands out of this whole classification here. So let's take a look at the land cover. And the first thing I'm going to do is I'm going to go into my raster calculator here. You can see in the raster bands here, you can see that there is an entry in here for each one of the raster layers that's in my layers selection here. And then you're going to see this @1 behind each one. That's because these are single band images. If this were a multi-band image, you would see multiple entries in here, and it would be at band 2, at band 3, whatnot. So, regardless, so for right now, we've got single band images, and I want to go ahead and I want to pull out the wetlands out of 2001. And again, going back to my legend, I can see that wetlands isn't just 95, but it's actually 90 and 95. There's two different kinds of wetlands, but I'm going to lump those together. So I'm going to go ahead and say where 2001 equals, I'll double click that, where that equals 90, then we're going to say or where 2001 equals 95. So the syntax here is important because what's important to remember here is that the or statement is a very inclusive kind of statement. It's saying that where the value is 90 or it's 95, we're going to choose both of those together. If I were to accidentally say, as I almost did, where 2001 is 90 and 95, it would be looking for some pixel in the layer there where both were true. And that's not going to be the case for any place here on this map. So we just need to have it where either case is true. Either it's 90 or it's 95. Or is a very inclusive kind of operator to use. So we're going to use or. And I'm going to go ahead and let's specify my output here. I'm going to go on into my module 5. And when I go into module 5, I'm going to go ahead and specify this as my wetlands 2001. I've already run through this once for some practice, so I'm just going to be rewriting my names. But you'll see I'm calling this wetlands 2001. And I go ahead and run that, and this is sitting behind, and there we go. So now I can see I have a yes or no, either or kind of value depicted on here, and this is where the value in the 2001 layer, if it's white, then it was wetlands. So let me go ahead and run the same raster calculator here for my 2019. 2019 equals 90, or 2019 equals 95. And again, this is going to be wetlands 2019. And so now I should have wetlands 2019. If I toggle between the two, you can see, oh yeah, there's some changes going on there. So some places where wetlands shows up in one and not in the other. Okay, very good. So now I'm in a position here where I can go ahead and start looking for changes in the wetlands conditions between the 2 years. Okay, so let's go ahead and take a look at our raster calculator one more time. And I am going to go ahead and show, since the value is 1 if it is wetlands for that year, and the value is 0 if it is not wetlands for that year, if I want to find a place that lost wetlands, I want to see something where the value of 2001 is greater than the value of 2019. Okay, because again, in this case, the value was 1 and now it's 0. So if the value of 2001 is greater than the value of 2019, then that can only mean that that is a lost wetland pixel. So I'm going to go ahead and I'm going to specify that this is wetlands lost. Okay, so wetlands lost, and go ahead and run it. And that is not the value I expected, so what did I do wrong? Let me try that one more time here, because that is, we did not lose that much wetlands. Let me go ahead and remove that layer because I have done something wrong. Run this raster calculator one more time. GIS is a science, but there's plenty of room for error and mistakes in here as well. So let me go ahead and try this one more time. So this, where this is greater than. Oh, that's what I clicked on the wrong layers. I'm clicking on the LCD. I need to be clicking on the wetlands. I'm an idiot. Okay, so where wetlands 2001 is greater than wetlands 2019. Of course, that's how that's supposed to look. So let's go run that. That's something much more what I was expecting. Actually, that is not what I'm expecting. Because I see here 0 to 0, but we knew from toggling between the two, that their wetlands actually were lost. So what's going on here? Well, let's take a look at the properties here. And the problem is in the way that it renders values in this on the screen here. I actually know where the issue is here, and it's under these the min max value settings, and you can see here that under accuracy it is set to an estimate of the values. If I go ahead and pull this down and choose actual and I apply it, now you'll see that there are some little white points appearing here on my screen. Okay, so the reason for this is so what we're seeing on the screen is not actually what's in the value or in the file. It needs to be kind of resampled and rendered a bit in order to show up on the screen. And so what we're dealing with here are just screen display settings. It actually doesn't have anything to do with what would happen in analytical space or what's written on the file. It's just a matter of what's showing up on the screen. And in this case, it was set to run on an estimate value rather than the actual value. And this would make sense if we were dealing with a very large raster, but since it's such a very small area, there's no reason to run with an estimate. We can go ahead and run with the actual values. We'll be dealing with some larger rasters a little bit later on in the semester, but for right now, let's go ahead and run this in an actual rendering environment, and that will allow us to see our output. So let's go ahead and run our calculator again. And so now I want to see the wetlands that were gained. And so I'm just going to go ahead and reverse that. And so in this case, I want to see where 2019 is greater than 2001. Again, it's a 1 in 2019, but it was a 0 in 2001, which means that that is a wetland gained. Okay, I'm going to go ahead and run that. Again, similar issue here. And I'm going to go into my settings and set that to actual. And there we go. So we can see that they look a little bit different. I've got some areas that were wetlands gained and some areas that are wetlands lost. And then the last, of course, that I want to see for my statistics would be which areas are persistent. So let's go ahead and take a look at the persistent. And in this case, what I want to see is now I might, because I've been using the greater than statement, I might be tempted to go ahead and say, where is wetlands 2001 equal to 2019? But the failure there is going to be that this is just going to say where there was no change, whether it was wetlands or not back in 2019. And since most of the map is not wetlands, both in 2001 and in 2019, we will see that almost the whole page is going to end up positive in this regard. So that's not going to work for us. So what we really need to do is we really need to be running it against a test instead. And so we're going to say the expression is going to be where 2001 equals 1 and where 2019 equals 1. So if a pixel matches both tests where this one layer equals 1 and this other layer equals 1, now our output should be areas that were persistent. So I'm going to go ahead and call this wetlands persist. Run this. And there we go. We can see that, of course, the majority of the wetlands did not change between 2001 and 2019. This is, of course, what we'd expect. So this is going to be a little bit sloppy symbology if we're working with it like this, because for one thing, it's just black and hard to see, and it's going to be obscuring any kind of base layers that we may have behind it. So actually, I want to go ahead and reverse these, and I want to color the three different separately because so that I can see all three at once. So let's go ahead and go to our wetlands persistent, and we're going to go ahead and specify this as a unique value. Classify it. We're going to go ahead and classify our persistent ones as a nice a nice blue wetland value. But we don't need this kind of greenish blue, so I'm just going to go in here and I'm just going to go ahead and delete that 0. Okay, so that's going to give us much more what we want. And here we can see the wetlands gained kind of popping up behind it. So let me go ahead and I'm going to copy the style from here. And I'm just going to go ahead and I'm going to paste the style here. But in this case, I'm going to go ahead and I clicked on the wrong layer. I'm going to go ahead and change. So wetlands gained. Well, let's go ahead and call that green. That's a little bit of good news. And we're going to go on into here to style. We're going to paste the style here. And I'm going to go ahead and color this red. Red alert. We're losing wetlands in these areas. Okay, so we can see, if I can zoom into a single area here where we can see kind of all of it happening. Here we go. So here we can see some areas here where most of our wetlands are persistent from 2001 to 2019. We can see the red pixels here are places where wetlands were lost between the 2 years, and the green here is wetlands that were gained in the subsequent 18 years. So we've already done a nice little bit of analysis here. But what I'm going to want to do is I'm going to quantify it. And I don't want to quantify it for the entire area. What I'm going to want to do is I'm going to want to specify certain areas to look at so that we can do some comparative statistics between different areas of our study area here. So this is where we're going to go ahead and we're going to use our difference watershed. So I've already gone ahead and I've created this difference watershed. This is just as an example. Your process is going to be just a little bit different. Let me go ahead and bring this down below. And so now I can see that I've got a difference watershed here, and I'm going to use a tool called zonal statistics. So this polygon is going to define a zone, and then Q is going to go ahead and calculate the statistics of my input rasters here within the zone that we specify. So I want to run this, but there is one downside here, and that is that my difference watershed, if we take a look at its properties, is projected in NAD83, EPSG 4269. Whereas we can see that comes from, that is coming from 4269. That is coming from the West Fork DEM here, which was, of course, the source layer for creating that. So these are in a different projection system. These are in Albers conical equal area. I want to reproject. These raster layers to be in the same coordinate system as my zonal layer. The reason for this is when you're doing a lot of raster functions and you're overlaying things, they need to be in the same coordinate space because the analysis is happening outside of the map environment on a lot of these raster functions, if that makes sense. So the reproject on the fly is happening very nicely for our displayed map, but it's not necessarily happening in analysis space. So to make sure that we've got everything in the same analysis space, I'm going to want to reproject my raster layers to make sure that they are in the same coordinate system as my zonal layer. Now, you might think I can just go on in here and I can go into my layer CRS and just go ahead and set my coordinate to the new layer. I cannot specify and stress enough, do not do this. What that will do is that will merely go ahead and redefine what the coordinate system for that layer is without actually transforming the data. And then when Q is trying to do its analysis, it's going to think the data is in one coordinate system when it's actually another coordinate system. It's a great big mess. Q allows you to have easy access to this thing. It's one of my few complaints about Q is it is way too easy to get yourself into trouble by touching these coordinate system definition buttons. Do not touch these things. You can go here for reference. You can take a look. Not there. You can take a look at the properties. But please do not change the defined coordinate system here. Okay, this needs to stay the same. If we want to reproject these layers, what we need to do is we actually need to reproject them. So I'm going to go into my projections here. And I am going to choose the warp tool. Okay, so again, that was from the raster tool, projections, and I'm going to go to warp or reproject. If you're doing this in the ArcGIS world, this would be defined as just reproject. Okay, so what I need to do now is I need to reproject all three different layers, and it's the wetlands gained, wetlands lost, and wetlands persist. Of course, when you guys do this, you're going to be doing it with a different land cover. But we want to reproject these three to match the coordinate system of my other layer here, which is going to be in the 4269 coordinate system. So I can do this one at a time, or if I want to save myself a little bit of effort, I can go ahead and I can run this as a batch process. Now I want to make sure I cover this because this is something that might come in very handy for you guys when you are working on your semester projects. A lot of you are going to be doing certain processes to multiple layers, and I just want to point out that you can save yourself a lot of effort if you go ahead and you run some of these processes as a batch process instead. So again, if I just go from the tool here down in the lower left, I can see that I've got a run as batch process here. And resize some things so we can read certain things. And I want to go ahead and I'm going to go ahead and specify, I'm going to add this for 3 layers. So I want to do this for wetlands gained, wetlands lost, and wetlands persist. My source CRS should go ahead and be defined, but my target CRS I need to specify. And I'm going to go ahead and I'm going to choose this to go into 4269, so that matches the coordinates of my my difference watershed. Now you notice that this is showing up right here, but you can see that this is project CRS. So this is showing up in the pull down list because it's already been defined by having the project be in there. Now the resampling, this is something that's of some interest. I can't recall if I've covered this much or not, but the resampling method, because this is a categorical layer, something is either wetlands or it's not. There's nothing in between. If this is a yes or no kind of answer, we want to make sure that our resampling is set to nearest neighbor. If this were a continuous layer where it was, say, elevation, and at this pixel the value may be 150, and at this pixel the value may be 152, and because they're adjacent, there is some in-between value, which is 151, and it's okay if the computer goes ahead and does those statistics. In that case, you'd go ahead and you choose something like bilinear or cubic. But in this case, because it's an either or, we always want it to either be yes or no on this one. We're going to go with nearest neighbor. Okay. I'm not going to go ahead and I'm not going to worry about my target georeference units, but I do want to go ahead and specify my output files here. And I'm going to go ahead and just call them the same thing, except I'm going to go ahead and append 4269 at the end of these. So I've got my wetlands, and this first one is wetlands gained. So I'm going to click here just for a shortcut, and then I'm going to go ahead and just put on wetlands gained 4269. Good. And then my wetlands lost 4269. And my wetlands persist This way, when they're showing up in my legend, I'll be able to tell which is which. Okay. And now I can run that as a single batch process. And that should only take, oh, actually that took less than a second to run all those. Q is actually a pretty good environment for running raster analyses. Let me go ahead and take a look here. If I refresh this, where did my layers? Oh, I just refreshed that one. There we go. So if I refresh my module 5, now I see that they're showing up here. They didn't get put into here. There's probably a box I could have checked to make sure that happened, but in this case, I'm just going to go ahead and drag these on into the map. Of course, Q is a little bit random as to whether it shows them or not. And once again, I'm seeing my black symbology that I don't like, so I'm going to go ahead and just copy my symbology from one to the next. So I'm going to go ahead and copy wetlands persist. I'm going to copy my style and paste that into wetlands persist. Here's my copy style, wetlands lost. Paste that style and my wetlands gain style. Should make it visible on all of them. There we go. And so if I take a look in my area here again, so within my polygon, I can see that there is no wetlands gain, but there is a little bit of wetlands lost, and then the rest of the wetlands in there are persistent. The reason why I'm going to go ahead and do it with within a sub-basin, kind of a difference basin like this, is let's say that due to the wetlands that are lost within this subcatchment. So remember, we delineated this difference basin here because there was a difference in the water quality measured at this lower station compared to the water quality measured at this upper sample point. So we've delineated the area that could possibly be contributing deleterious material that's degrading our water quality between these 2 points because it was good in the upstream and not so good in the downstream. So this is the area that can be contributing to that. And if our hypothesis here is that the reason for that contribution is lost wetlands, now I can go ahead and I can analyze that I have lost these 3 pixels of wetlands compared to the rest of the wetlands in this area here. And so now I want to go ahead and I want to run some statistics. So the statistical tool that we're going to use is called zonal statistics. And I'm going to go ahead and I'm going to search my processing toolbox. You can see that there are multiple versions of the zonal statistics available. You might think that we want to run the raster layer, but actually the raster layer is specifying the input layer for the zones. And so that's not what we want because our zone layer is actually a vector polygon because that's the output from the model that we created a little bit earlier. So actually I just want to run zonal statistics. So I'm going to go ahead and fire up zonal statistics here. And to get the full analysis of what's happening here, I would have to run this multiple times or as a batch process, but I'm just going to run this for wetlands lost in this case. That should illustrate the method, and then I want you guys to go ahead and do this for gain, loss, and persistent for the cover layer that the cover type that you do. So I'm going to go ahead and I'm going to choose, and you can see the only polygon here is the difference watershed. My input here, I'm going to look at wetlands loss 4269, again making sure that my spatial layers are the same here. And in this case, I'm going to go ahead and put in for my output column prefix lost wetlands and then an underscore here, and that will make sense. Now I want to choose which statistics I'm going to calculate. I'm going to hit the three dots. And you can see that these are the different statistics that can be calculated within this polygon zone here. Okay. Now, the reason why this is zonal is I could have multiple polygons within the same layer, and it would calculate them separately for the different zones. This is actually a very nice tool. In this case, there's only one zone in this polygon layer, but I could have multiple polygons within that zone. So let's go ahead and I'm going to uncheck count, because I don't need the count of the number of pixels that are within there. But I do have the sum, and the sum is going to be interesting in this case because I do have I have a value of 1. And so this is going to sum up the total number of cells within this zone that have the value of 1. And the value of 1 in this case is wetlands that were lost. Similarly, if I throw in the mean, well, that's going to give me the mean of the values within the entire zone, and given that it's either 0 or 1, that's actually going to give me a value of essentially the proportion of values that are 1 within this area. So hopefully the statistic will make sense to you after we've run it. So let's go ahead and run this. And this is going to give me an output here, and I did not specify. This is go to file, so this is actually coming out as a temporary file here. And let's go ahead and take a look at our attribute table here. And we can see that we've got our lost wetlands sum is 3 pixels, and our lost wetlands mean, if we go ahead and we take a look here, that this would say, if we divide this by 100, we can see that this would be about a 1/20% of the total area. And yeah, that's possible, I suppose. It maybe seems a little bit low, but yeah, I'm at 1/20%. Yeah, actually, no, I'm going to backtrack my hesitation. That looks about right. So if I go ahead and, once again, I'm going to be taking a look at my attribute table here, and here's where I'm going to pull the statistics out. And this is my lost wetlands sum and my lost wetlands mean. Now, what the method that you're going to do for your assignment for this one is you're actually going to go ahead and take these values and compile them into a table. I'm actually not even going to ask for a map on this one. I'm asking you for the results of your analysis, and the communication of those results does not have to be map-based. So in this case, what I'm going to ask you for is a table that explains your results, not the map. Okay, so just because the analysis was done in a spatial context does not necessarily mean that the communication of your results has to be. Okay, so you're going to go ahead and you're going to create a table that is going to tell me the gained, the lost, and the persistent cover type, whichever cover type it is that you choose, within the areas that you're going to delineate. And let's talk about the areas that we're going to delineate here. So Sam, in addition to being an excellent researcher and everything, is actually also works in the real world in water quality, and has actually working with water quality folks up in Big Sky. And this is all derived from data that he's working on for some water quality projects up there. And there is concern in Big Sky about the degradation in water quality along, again, this whole river system here is the West Fork of the Gallatin River. And confusingly enough, we have forks of the West Fork. So this here is the middle fork. If you're following my mouse here, this is the middle fork of the West Fork of the Gallatin, and this is the South Fork of the West Fork of the Gallatin. And then, of course, this actually splits into, there's the North Fork of the West Fork of the Gallatin. So I'm going to ignore the whole West Fork of the Gallatin, and for right now, we're just going to talk about the Middle Fork and the South Fork here. And to give us some context here, let's go ahead into our web menu, and I'm going to go And let's go to the OSM standard. That's a nice enough map. And now we can see the developed area here in Big Sky. And so the areas of concern is that there is actually a difference in water quality that has been observed. And this is true. There's been a difference in water quality observed on the Middle Fork compared to the West Fork. Go ahead and turn off these wetlands for right now. So we want to go ahead and we want to run our land cover change statistics separately for the Middle Fork versus the South Fork here. Okay, so that means we need to go ahead and we need to delineate different basins for these two forks here. Now we're only really concerned about the areas that are kind of under development pressure here within the Meadow Village area of Big Sky. So I'm going to go ahead and I'm going to close out my search here. I'm going to turn off the vectorized and turn back on the thinned layer because this is tied again to my input layers for my model. And I'm going to go searching for my model again. There it is. I'm going to go ahead and I'm going to run my difference watershed. Again, my input for flow direction is going to be the drainage direction. And let's go ahead and delineate a difference watershed for the Middle Fork first. So let's go ahead and do our output. And I'm going to zoom in here. Here's where the two come together to become just the West Fork of the Gallatin. But if I choose this point right here, so that point right there is the lower outlet point for the Middle Fork. I'm going to zoom in out here, and so we've got the Meadow Village area here, and if I go ahead and zoom in on here, here's where the North Fork branches off. And I don't want the North Fork area, and you can see that there's this brownstone loop area here. Go ahead and give yourself some sort of a background raster so you can see this. And I'm going to go ahead and choose this point just downstream of where the North Fork comes into the West Fork here, or comes in the Middle Fork. So I'm going to go ahead and click on that. Need to get rid of that. And I'm going to go ahead and specify my output here because I actually do want this to be persistent to go to a layer. So I'm going to go ahead and I'm going to save this difference to a file, and I'm going to call this is the Middle Fork Basin. Okay, so I'm going to go ahead and call this the Middle Fork Basin, and I'm going to run my model. And that should get added into the map, and there we go. Oh, very nice. So there is the basin that contributes flow to the West Fork, or to the Middle Fork of the West Fork of the Gallatin. Now let's run this one more time. I'm going to go ahead and run my model again. And this time I'm going to run it for the South Fork. So let me go ahead and specify that this is my pour point here for the South Fork. And I want to choose my upper point. Again, we're really just concerned about the kind of the town area here. And if I zoom in here, you can see where there's this other stream coming in to the South Fork. I'm not really that interested in that area there. So I'm going to get to just downstream of this other stream coming in here. Out here by, well, you can see this Usu Falls Airport. If you're familiar with Big Sky, you know that's, now there's like a grass strip there. It's not really a thing. So, so I'm going to go ahead and I'm going to click on this as my upper. And I'm going to go ahead and I'm going to run it. Oh, I want to specify my output to a file. And I'm going to call this the South Fork Basin. These are names that I'm choosing so that I can keep straight what's going on. Make sure you're naming it something sensible that you can keep straight. Just be sure that you can tell the difference between the Middle Fork and the South Fork. So let's go ahead and run that. Oh, and look how nicely those two catchments kind of nest together. And in fact, if I go ahead and I toggle them on and off, I'm going to see that there is no overlap. What we don't want is we don't want areas that are part of both catchments, and it seems like we've done a very nice job. I don't see any gaps or anything here. So this is good. So we've delineated our two basins here. So now what you guys are going to do is you are going to go ahead and choose your own land cover. You're going to delineate your two basins there, the Middle Fork and the South Fork. And I want you to go ahead and run your zonal statistics of the gained cover, the lost cover, and the persistent cover, and compare between those two catchment basins and tell me what statistical differences that you can see in the change in land cover between the Middle Fork and the South Fork basins. Okay, so if this seems a little vague, feel free to give me a shout out, and I'd be happy to meet up with you. Don't forget that I do virtual office hours. That should be posted up onto the D2L. And if you want to join in, otherwise, I'm happy to go ahead and set up a one-on-one meeting with you guys, and we can do a screen share, and I can take a look at what's going on. But hopefully this one is fairly straightforward. Fingers crossed the video quality is going to be a little bit better than the last one. I apologize for the jerkiness there. And let me know if you guys have any questions. And apart from that, I'm going to keep on reviewing your proposals for your semester projects and start thinking about your different data sources and methods like this that you might be able to apply. Okay, so have fun with it, and let me know if you have any questions.